What I would like to do is first introduce myself a little bit more from the perspective of this particular talk, and then consider, given the history, what can history of flooding on the Elkhorn River in particular say about chances of flooding in the future? And then talk about another approach, model predictions, and this is where the system science comes in. And then last, talk about the relationship between risk and mitigation. And then finally, questions. And I think the way we're going to handle questions is you can open up your chat window and enter your questions there. So what is systems science in a systems perspective? Well, if you look at an image of the Elkhorn River like the one you see here, you start thinking about how those cliffs are a sediment source and the influence that has on the river. You start thinking about how water is exchanged between the river and the groundwater. And you start thinking about the vegetation and how evapotranspiration moves water back into the atmosphere. There, you start thinking about everything you need to think about in order to understand how the river behaves, and in particular here, what contributes to flooding. So it's sort of the water cycle, the biology, the human activity, everything together, very multidisciplinary. Okay, so who am I? You've heard a little bit. I do own a shack on the Elkhorn River. This is what it looked like right after the flood this last year. I also teach environmental and physical geology as intro courses. I love to paddle. I've paddled about 100 miles of the Elkhorn River. If you ever have a chance, you should definitely paddle it. It's nearby. Really nice paddle. And my specialty in research has nothing to do with flooding. It has to do with rock fracture patterns. So mainly what I'm going to share is what I've learned from my teaching perspective. Also have 5 kids, 3 of who will be at UNO this next fall. Okay, so flooding. We're first going to talk about what are the chances. And who wants to know? So what's the significance of trying to answer that question? Well, insurance companies for premiums, people buying property, should they buy that river property or not? In our case, it was because our little shack is elevated on telephone poles. There's a story to that, but that we thought would help insure against flood damage. Banks providing loans, planners who have to set policy, engineers building a bridge in a floodplain. How big does that bridge need to be? Natural disaster responders, floodplain farmers, the Army Corps, who also has responsibility and sets policy, and then very last, academics. So it's not a trivial question, and a lot of effort has been and is being put into trying to answer that question. So looking at it from a historical perspective, I think most of you realize, share that common experience that larger floods are rarer and smaller floods are more common there. Now, when we talk about a flood, the flood size, there are 2 different ways of thinking about that. The normal one is how high does the water get, the gauge level there. There's also the associated discharge, the volume of water that passes past a section of the river at any one point in time, measured often in cubic feet per second. And the 2 are related, strongly related, but there are other factors that mediate the relationship. And then flood size will vary along the river there because of those other factors. Now, most people have heard about the 100-year flood. I hate that phrasing, to be honest. It sends people down the wrong path. Instead, think of for a given size of a flood, a given discharge, what is the probability that's associated with that? And for the 100-year flood, basically what you're saying is there's a 1% chance each year that you'll see that size of flood or larger. So that's the way to think of it. We're in the world and using the language of probability and statistics. Now, one thing to realize is if you come up with an estimate for the size of a 100-year flood, that estimate has a confidence associated with it. Sometimes the data is pretty good and you have reason to think you have a good estimate, but sometimes not as good. And there are ways to quantify that estimate too. there. So if you're thinking about these things, you not only want to think of that number, but how well we know that number, what confidence we have in that number. So here's a basic way of looking at this that scientists use over and over again. A plot. In this particular case, you have x-axis as the size of an event. And then the y-axis is how often that event occurs, what frequency it occurs with. And as we said before, the smaller events occur more frequently, and the larger events occur less frequently. And if you can establish a good mathematical fit, that's what the red dashed line would represent here, you have some basis for predicting one given the other. The blue stars are meant to represent, data here. Interestingly, by the way, we use the same basic approach for predicting earthquake probabilities and volcanic eruptions and a whole suite of other natural phenomena. There's not just flooding. The specifics of how you plot X and Y differ. And we're going to use an example along the Elkhorn River, mainly because I am emotionally connected to what happens on the Elkhorn River due to this shack here. And so where do you get the data? And one thing I'd like to stress is that data is available to everybody. The URL is down here. And this is just a map showing all the different USGS, United States Geological Survey, stations in Nebraska, which you can get data from. And this is the specific station which I'm going to use data from and take you through a quick analysis there of the historic behavior and then what that might imply about future behavior right there. And that, of course, is the gauging station, the USGS gauging station, directly upriver from this stretch of river I'm on right now. You can get the data in many, many different forms. It's actually very rich, different types of data and in different forms. And this is a simple plot showing the record from before 1904 to present of the annual peak discharge, the largest discharge you had every year. Of course, the higher the little blue dot, the higher the level of the river was, and at some level it's flooding. And notice this one lone dot way up here there. So that's the type of data we're going to analyze. But you can also get much finer grained data. This is data of the daily discharge over the last couple of months. This big peak here is the flood of 2019. One thing that you should realize when you read this data is that sometimes a log axis is used. And when you have a log axis, then every increment is a multiplication factor, not an addition factor. So 1,000, whoops, let's go back here. 1,000, 10,000, 100,000. So if you look at these two different peaks here, this peak here is actually 10 times larger than this, even though it only looks like it's maybe 50% larger or 60% larger there. Okay, so this is some more of that fine-grained data, but this is now the height that was measured of the water at that USGS gauging station. We know from experience that right here at the shack, if it gets over 16 feet or so, then it starts flooding. So you see that 2019 peak was substantially higher than you needed to have flooding. Okay, so this is a traditional type of plot used to estimate the 100-year flood. And basically what we have here on the x-axis is the recurrence interval. It's a frequency. It's a little, again, non-intuitive. One here represents a 10% yearly probability. So every year you have a 10% probability that you're going to see a discharge 40,000 cubic feet per second or larger there. The y-axis is the size as measured by discharge, the volume going past that gauging station at that time. And a lot of programs now, and even Excel, which is what I did this in, will provide you a statistical best fits. So this blue dotted line here is the best fit line. This is the associated equation. So we can use this equation to predict the size of the discharge given a recurrence interval, a probability we're interested in. 1 here would be a 10% probability, and 2 would be a 1% probability in a given year. This R squared is basically a measure of how good that fit is. And this will give you a clue as to what type of confidence to have in that mathematical relationship. If it was 1, it'd be perfect. The lower it gets, the less the quality of the fit between the line and the data there. Okay, one thing to notice is we've got 2 events that are larger than what we would predict for a 100-year flood, which would be 83,000 cubic feet per second. So why? And it could be bad luck. Sometimes you just have bad luck and you get larger floods than would be statistically predicted, or it could be flawed analysis. And so a basic assumption here that's really important in this whole approach is that of historical continuity, that the system is going to behave the same in the future as it did in the past. And of course, there are reasons to question this. You just go to the central part of Nebraska, and there are the sand hills. And those are dunes. They're now vegetated, but they used to be like the Sahara. So it used to be much drier. So how can we analyze for this continuity of behavior, knowing that maybe we shouldn't expect it? And one thing to do is to look at it within the record and just maybe look at the first half of the record versus the second half, take it through the same analysis, see if we get different answers. And this is what's been done here, and we do get different answers here. Here is the plot with the best fit line, and basically it makes a 15% difference if you use the first half versus the second half. It suggests that something has been changing with time. You need to do more analysis than just this, but it's a strong suggestion that the river over the period of record that you have, the history that you have, is not maintaining its behavior. It is changing in some fashion. And of course, you can ask why. And one good possibility is a change in climate. And that can either be cyclic, and I have that in quotation marks, up and down, but with no long-term drift. The average stays the same overall with time. Or you can have longer-term drift, something that you might call climate change. Something is fundamentally changing with time over the period that you're thinking about, 100 years, 1,000 years, whatever. The other possibility is a change in a hydrologic landscape. Obviously, if you put a dam upstream, things are going to change. You're not going to see those smaller flooding events because that water is stored behind the dam. Levees also influence things. Urbanization, because you change the way the ground soaks up water or not, will influence the hydrologic landscape. Farming practices, so Nate might be able to talk a lot more to this there, but there's literature that suggests that the runoff from agriculture, of course, there's a lot of in the Elkhorn River Basin, influence how much runoff you get. Logging doesn't happen much in the Elkhorn area, probably not at all really, but in areas where it does, that also changes how water runs off the landscape or is soaked and so forth. So those things can make a difference too. So where can we get a longer term history? This is a complicated plot, but basically you're looking from 900, the year 900 to present. And this is a drought index. And if it's greater than 0, it's wetter. And if it's less than 0, it's dry. And the key thing here is this is based on tree ring data, and it gives us an idea of long-term variation. And you can see the ups and downs. And you can see that sometimes it's down for significant periods of time, that you can have droughts that might last several decades in the extreme there. So that would suggest we need about 200 years of flood record to really capture this variation. And remember, we only had about 90. So that comes back to thinking, okay, that historic record can give us some idea, but we have to think about this more complexly. The longer the history you have of flooding, the better you understand the behavior and the better you can predict. So where can you get that longer history? We've already talked about tree rings. I'm just introducing this quickly as a thought path one could go down. We won't have time to go down it, but there might be places in wetlands and lakes where there are sediments from floods that are deposited that can tell us something. Okay, so we're gonna switch gears here now. There isn't this additional approach. You can model it using a systems perspective. Think about flood size, and then think about all the factors that influence flood size. If you can get a handle on all these factors at any one point in time, then maybe you can predict what the flood size will be. So the amount of rainfall is obvious. The area that the rainfall covers is also crucial. How fast the rain comes down turns out to be quite crucial, because that determines whether the ground has time enough to soak it up or not. So the longer it takes for that rain to fall, the better. Snow on the ground, that can be important. How fast does it melt? Is the ground frozen? That was the big factor in 2019. The ground was frozen. It wasn't going to be soaking up any of that water. The amount that the ground is already saturated, the seepage traits of the ground. Then there are other factors like the channel configuration of the river channel itself, and that can be particularly important for local flooding. And then upstream storage in the soils, in dam basins, in wetlands. Where might that water be stored instead of rushing downstream, adding to the flood? One thing about this approach that's a huge advantage, it allows for short-term predictions, not this probability, oh, next year we have a 1% chance of a flood this size. Instead, it allows us to say, in the next week or two, we may have a high probability of a chance or a high probability of a flood this size there. Okay, so what do these system models look like? They depend on computers. They get really complex. Here is just one schematic that I grabbed off the web of one of the map models. And you can see that it looks a little bit like a water cycle model. I assume most of you have some feel for the water cycle. My students all tell me that they were introduced to it in grade school, which is great, they should be. So you can see snowpack here, you can see soil moisture here, there's deeper groundwater reservoirs. Those can be connected to the streams and so on like that. This is probably a better depiction of a very powerful approach, but it depends on a lot of computing power and a lot of input data, and that's a finite element model. For every one of these little squares, the slope is prescribed so that you know how fast water would run off of that. The seepage characteristics are prescribed so that you know how the water would sink in with time. And then you can have a rainfall event that you have input onto this model and so on like that. Now, USGS does a lot of this type of modeling. One for longer term predictions is called GSF Flow. This actually will work on a decent computer. It is free. You can download it from the USGS. However, the agency that has primary responsibility for flood prediction is NOAA. They work together. USGS and NOAA work together. And you can find more information here. And they use these type of finite element models where they're putting together the rainfall event or the precipitation event, the snowpack that's there, along with all of these ground characteristics, the slope and the seepage characteristics, to actually model, to quantify what the flow will be out of the system at any one point in time. I should say that those models are in their infancy, and they will they need a lot of work to get better, but they are very promising. And in some places where the effort has been taken, produce useful predictions. This slide is just to make you aware that there are other approaches. There's something called fuzzy models. It's sort of expert knowledge that you capture as rules. That's what the rules look like when you codify them. And then you can build predictions. This one's actually for risk associated with flooding. And these models can be trained by historical data. So a point I wanted to make here is that this isn't instead of, but in addition to looking at the historical data. And there's a lot of interplay between the historical data and these models. You can test the models with the historical data. Okay, getting close to the end here. The last major point I wanted to make. Risk is equal to the probability of an event times the cost of the event. A lot of people immediately recognize the element of probability. They often aren't as familiar with the element of cost in risk. And event size and cost are positively correlated. So bigger floods produce more cost, more damage there. So there's mitigation. That's where you reduce the risk in some way, building a dam, building levees. A key thing about mitigation is that it's different for different size events. It preferentially reduces the risk for smaller size events. It may not change the risk at all for certain larger size events, those more infrequent events. Then here's the kicker: lower risk leads to increased human presence. That means just human nature there. High risk areas people tend to avoid. If they begin to think that this is a lower risk area or are told, then they will set up shop there. That increased human presence, by the way, then increases the cost of the event and therefore increases the risk. So you end up with the situation where mitigation can cause risk from larger and rare events to actually increase, while those from smaller, more frequent events shrinks there. So this whole thinking about risk with time and what you should do and what policy you should have for floodplain is an evolving sort of situation. And in large part because as you mitigate, you change perceptions, which changes human behavior, which changes risk. Okay, main takeaway points here. A lot is at stake. It's worth the effort to think about these things. Larger floods, less frequent, cost more. Historical record helps. The data is freely available to all, including you. So if you want to sit down and play with this data, something I love to do, you can learn how to do that. You can get the data. Computer modeling and system science is providing increasingly good possibilities of short-term forecasts. This is still developing. NOAA is the agency in the US that is pushing this forward, and they're often working with other people. And finally, mitigation can reduce risk for small events, but increase the risk for larger events. So that's it. Don't worry about that. I will stop share for the moment. Okay.
Thank you, Harmon. That was incredible. Thank you for that wonderful knowledge. We do have a few questions.
Okay.
Let's see, from Karen, she asked, who is making all those real-time measurements such as soil saturation in urban versus rural?
That's a very good question. They use remote sensing a lot. So the remote sensing can identify different landscapes. There's this whole science of classification. And then you don't have to measure every little bit. You measure an example of that sort of type of land surface. For urban setting, a sidewalk, you can assume that's going to be impervious versus a lawn and so forth. But you could also have agricultural field versus a natural prairie versus forest or so on like that. So you use the imagery to classify. You measure some samples for each one of those classes, and that goes into the model.
She also said, so levees, as seen on the Missouri, have created as many problems, Bellevue, as they've solved.
Yeah, levees are tricky. They're a good example, by the way, where for small floods, they're good at mitigating. For larger floods, when they fail, you know, then because of the perceived lower risk, you know, the cost can actually go up. Yeah, levees are tricky. One of the important things about levees to consider is the setback distance. So the setback distance is from the main channel. How far away is the levee? The farther the setback distance, the more room you have to store water there. So the less likely the levee is to be overtopped. If you have your levees too close to the channel, then you don't have that room, and for the same size event, it can go over the top and take out the levee. But if you've got a high levee setback, that's land you can't plant, or not in the normal fashion there, or you wouldn't want to have any structures on.
Awesome, thank you. Another question from an anonymous attendee. Do you have any suggestions for introducing systems thinking in the context of climate change or flooding to the general public?
Ooh, yes. But that's not a simple question. What I might suggest is it's be one I'd be quite willing to talk at length about, and maybe we can share my email, and in that way that person can contact me. There are many resources, though, to try to get Earth system science across. Yeah, many different, and it would depend on your audience. You know, are you talking about grade schoolers, high school students, educated lay people, etc.? It very much depend on those. So good question. I'm afraid I don't have an answer that will fit the time available here.
Well, Harmon, if you could maybe post your email into the chat, just so people have that, that would be awesome.
Okay, will do.
Another question from Dallas Polivka. He's asking, is it possible to get a copy of this PowerPoint from you? It would be very helpful with the links.
Yes. So there's my email. Send me an email. I'll be happy to send you a copy of the PowerPoint.
Awesome. And the last question, will a recording of this presentation be available? It will be on our Facebook page, the event. Harmon, I had a question. I was wondering if nowadays, with all of the new technology, do they ever utilize drones to produce the models, such as the finite element models?
Yeah, so again, a good question. Absolutely. The finer the resolution of your data, the better the model, but also it is much more difficult to run. Before you know it, you need supercomputers, right? But what the drones can do is provide that finer resolution data cheaply. I'd have to think about, it's a good question about its specific use in trying to gather data for those finite element models there. I do know that drones are changing the way that we do research and work because they're cheap. That turns out to be quite important. And then you can get high quality data. And I don't know if people knew this, but there's now this pretty robust software where you can turn that drone imagery into three-dimensional scaled oriented models there. There's another type of data called LiDAR, and there is detailed LiDAR data, but that has advantages in terms of resolution, disadvantages in terms of how it can see differences, basically.
Very awesome. Oh, Karen said into the chat, the NRDs are committed to using the best science possible for meeting their charge to implement flood control for their districts. Do you know if any NRDs are currently using the systems modeling for their projects?
I do not know. What they might do is depend on NOAA for that. That I do have a link to the NOAA site for flood forecasting there. And it is expensive to develop and run these models. So it does make some sense to centralize that in some part. But it's a good question. Again, probably best to ask the NRDs.
Mm.
But I
All
wouldn't be
right.
surprised if they aren't sort of depending on NOAA's efforts. And USGS is also involved too.
Awesome. Thank you. Thank you, Harmon, so much for all those answers and for all that knowledge that you just taught all of us. Incredible.
My pleasure.
If no one has any more questions, we will move on to Nate Dorsey.
Sure, thanks, Dakota. I'll go ahead and share my screen as well. I also have a presentation that I can share. So I'm going to talk a little bit more about the effects of floods on agriculture and farming specifically, and talk about how farmers can recover from the effects of floods. So a little bit about me. You heard a little bit earlier. My name is Nate Dorsey. I have a master's degree in agronomy from Kansas State University. I'm also a certified crop advisor with the American Society of Agronomy and a certified precision ag specialist with the American Society of Agronomy as well. Most of my career has been in supporting farmers with technology adoption. So focusing on precision agriculture technology. In my career, I've had the opportunity to live and travel all over the United States. So I spent some time in the Dakotas, also Hawaii, Arizona, Kansas, and now Nebraska, primarily working with farmers with technology adoption. I'm currently the manager of agriculture technology at Valmont Industries, also known as Valley Irrigation. In my current role, I manage research and development of new irrigation technology. So the primary focus is developing tools that help farmers make better decisions about how to manage their water when it comes to irrigation. So it's a lot of fun. I still get to travel quite a bit, so spend quite a bit of time in Nebraska, but also travel domestically all over the United States and internationally as well. So I thought it would be great to start with a map to give some perspective of the flood and the effects that it could have on farming. This is March 2018, so this is the year prior to the most recent flood. And you can see that there's pretty well-defined river channels with the Missouri River and the Elkhorn and some of the others, the Platte. So, pretty well contained. But when we look at what happened last year, we can see just how big the flood was and how much water really spilled out into agricultural land. So when you look at the Missouri River Valley, but also the Elkhorn River Valley specifically, there's a lot of farmland that was affected. And the water stayed there for a long time. So that can have a big effect on farming. So I want to talk about a few of the different types of effects that we see in agricultural land. And there's some immediate effects. There's also long-term effects that we'll cover as well. Some of the immediate effects that we see would be loss of property, soil erosion and deposition of sediment, things like prevent plant. So when farmers can't go into their fields and plant the crop for the season, but also damage to crops that have already been planted. So we'll dive into each of these in a little bit more detail. The first and probably the most obvious is the loss of property. So I think this is probably one of the most heartbreaking parts of floods, at least initially, when you're driving by an area that's been affected and seeing houses or equipment, grain bins underwater. And this was something that definitely struck me driving between here and Kansas City through the Missouri River Valley. The floodwaters stayed there for months, and grain bins were exploded. Once the grain had soaked up the water, so they had lost obviously their source of income for that season, but also anything that was stored in grain bins, equipment, houses, other structures on a farm, and that could be pretty devastating. And last year, I know that the effects of that on farmers was in the hundreds of millions of dollars. Another effect is soil erosion, and this can also be pretty devastating. It might not be as obvious initially, but whenever you have running water, that can move significant amounts of soil. Here we can see things like rill and gully erosion. And for farming to take place in those fields, again, they need to be repaired. So you have to think that farmers have to be able to move equipment back and forth, things like planters, sprayers, combines to harvest, and that can't be done if there's significant areas of erosion in a field. So there's a few different ways that that type of damage to a field can be repaired. Farmers can use land leveling equipment or tillage. So when you think of land leveling equipment, I most commonly think of things that would be used in the construction industry. When they're preparing a construction site, they have those big earth movers that they would pull behind pieces of equipment that can be used to fill in low areas or places that have had significant amounts of erosion. Tillage can also be used to help smooth surfaces. The biggest thing for farmers is that they need to avoid being in the field when it's still wet. So they have to wait until the water has receded and the fields are dry enough for them to go in, so they can to help prevent and avoid soil compaction, which can also have some very negative effects on crop growth. If the damage is severe enough, that can take that field completely out of production. In those cases, there are conservation programs that can help farmers, so that land can be taken out of production and put into things like wildlife habitat. And that does happen. When you have really severe gully erosion where gullies can be 10 or 15 feet deep, that's in most cases not fixable. Also, the loss of topsoil can result in a permanent loss of crop productivity. And it doesn't take much to lose your topsoil. That's usually just the first few inches of soil on top. And if that is lost in a flood event, that can have a significant impact on farming and crop yields. So another immediate effect is deposition. So we can have large amounts of sediment that are deposited on fields. This could be sand, this can be organic debris, things like crop residue from neighboring fields. It can be other sources of waste, from structures that might have been destroyed upstream. So there can be a significant amount of material that is deposited on a field. And this can range from just a few inches deep to many feet deep. So I've heard of cases where you have sand and other deposits that can be 10 to 20 feet deep on a field. And that can be a big problem for farming that land in the future. So really, in this case, you have to evaluate that deposit to figure out what's the correct response. So usually the first thing that I would recommend doing is figuring out, how deep is that, but also is the underlying soil and topsoil still intact? Or in other words, has this just been put on top? Could you either remove it or work it into the soil? The other is how deep is it? This will also affect what the correct course of action would be in the case of a flood deposition. And the other one that might not be quite as obvious is if there are any contaminants in that sediment as well. So there could be things like oil or other pollutants that might be in that would make it unsuitable for leaving in place or even removing, and how you want to handle that. So there are a few ways to handle that. One, if it's not too deep, it is possible to incorporate that into the soil through tillage. And the University of Nebraska actually does have a calculator that you can put in the depth of any type of deposition or sand, and they will spit out a recommendation for how deep they would recommend incorporating that. So is that 8 inches, 10 inches, or deeper, or is it best to just remove it? If it is removed, there are also a few other options. It can be taken to a landfill. A lot of landfills actually use sand and other material to cover trash that is put into a landfill. There are possibilities that it could be repurposed. So it could be piled up in a certain area. It could be used to treat roadways for snow, or it could be used in other things like cement. But it really depends on what exactly the characteristics of the deposition of that material. In some cases, permits can also be issued to return sand to the river that it came from. I'm not the biggest fan of that option, but it is an option that can be taken in some cases with the right regulatory approval. Another effect is prevent plant. So in the event of a flood, especially in the springtime, that can prevent a farmer from planting a field. And the Prevent Plant program is administered by the USDA's Farm Service Agency. And they do have deadlines for this, and they are state specific. So in Nebraska, the date is May 25th for corn and June 10th for soybeans. So in the event of a weather related occurrence, especially something like a flood, if a farmer is not able to plant, for example, corn by May 25th, then they could get an insurance payout for that. I think that in these cases, I think it's tempting to, after a flood event and using the Prevent Plant program, to leave that ground as it is and just wait for the next season. However, I think that it's really important to not leave any field bare. So I think cover crops are really an important thing to consider in these types of cases. They can help prevent additional erosion, so through water or wind, but also help with things like soil health and getting a field ready to be farmed again the following season. And I'll go over some additional benefits of cover crops here towards the end of this presentation. Another effect is damage to growing crops. So this can be especially devastating for a farmer if they've already made the investment in seed and the time and to plant a field, but also with things like crop nutrients and crop protectants. Having a flood that would come in sometime during the season can also be devastating for a farmer. And with this, it really depends on the amount of time that crops are underwater. If that's a few hours or a few days, they will likely recover. But if we're talking weeks to months at a time, a farmer could really experience a complete and total loss of that crop for the season. And this is primarily because crops, while they do breathe in carbon dioxide and respire oxygen, their roots are actually, they breathe oxygen. So in the event of a flood, water has very low dissolved oxygen content. So roots underwater will basically drown. They'll asphyxiate. So again, this really depends on how long that crop is underwater. And also a temperature can be a factor as well. So, with cooler temperatures, a crop can usually survive that for a longer period of time. But with warm temperatures and water that's covering the crop for a few days even, that could cause a significant crop loss. So we went over some of the immediate effects, but there are also some long-term effects of floods. And these can be things like the loss of soil nutrients, the effects of flooding on soil ecology, and just depressed yields. And farmers can experience depressed yields in the field for several seasons after a flood. And we'll talk about some of those reasons. So the first is the loss of soil nutrients. And there are certain nutrients in the soil that are what are considered mobile nutrients. Probably the most notable would be nitrogen in the form of nitrate and sulfur in the form of sulfate. And during a flood, a significant amount of water will move through the soil profile, and those mobile nutrients will move down with the water, often way beyond where the roots can reach it. Also, in flooding conditions, you can have other processes such as denitrification, where in anaerobic conditions, bacteria in the soil will use nitrogen as an energy source and then release it in gaseous form. So you might have the release of nitrogen in the form of dinitrogen, which is the most common form of nitrogen that we breathe in the air, but also forms like nitrous oxide, which are significant contributors to greenhouse it's a greenhouse gas and can have significant effects to global warming. So those are a few things that can cause significant losses of nitrogen in a farming environment. So this is a common picture that you might see for an area of a field that's been flooded or might have ponding issues. Typically the crops will be stunted and have a lot of yellow leaves. This is primarily for those two reasons that I talked about before. One, the roots of the crop not getting enough oxygen, but also in those areas losing nitrogen from the soil. And so you can imagine that an entire field that's been affected this way can have a significant impact on any crop that was planted there. Another long-term effect is the effects of flooding on soil ecology. And there's been a lot of research on soil health and the effects of soil ecology on crop growth. And I think that it's quite apparent the benefits that soil ecology has. One of the first ones is fungi and their associations with crops. And most well-known is our arbuscular mycorrhiza. And this fungi basically colonizes the roots of crops that are growing and really can effectively increase the surface area that crop can scavenge the soil for water and nutrients. So the fungi will reach out into the soil and get water and other nutrients and bring it back to the roots of the crop in exchange for sugars that are produced during photosynthesis. And fungi have significant effects on things like soil health and soil structure and improving how water can flow through soil. Another is bacteria. These are also really important to soil and crop growth, breaking down organic matter and releasing nutrients that crops need to grow during the season. There's also microfauna, which are very small organisms, but also similar to bacteria, break down organic compounds and release nutrients, and also can help improve soil characteristics. And then macrofauna, things that we would think of that we could see more easily, like earthworms, that also have significant effects on soils and how water can move through the soil. When there is a flooding event, all these organisms, fungi, microfauna, bacteria, macrofauna, they all breathe oxygen. So in the event of a flood, if that, a few hours or a few days, they can probably recover fairly quickly. But if we're talking, a significant flood where we might have standing water for weeks or even months at a time, it can really almost effectively sterilize the soil and have significant impacts on future crop growth and soil characteristics. And all of these things together, so the loss of topsoil, the deposition of material on top of a field, lack of oxygen to growing crops, and loss of nutrients and soil ecology in a field, can really have an effect on yield, not only that the year that there is a flood, but also in the future. And so this graph is just a representation of what that might look like. This is not real data, but you might have an average yield for a field, and that might go to 0 during a flood year. But for the seasons following a flood, they typically will not be at the pre-flood levels. It can take several years for that field to recover. And that's things like loss of topsoil or nutrients, or the effects that a flood can have on ecology, can all contribute to that. So when it comes to helping mitigate a flood, especially if a field is in a flood-prone area, there are a few recommendations. One is to implement practices that will help slow down water, and this will help prevent erosion and deposition on a field, and also try to find ways that will help increase water infiltration into the soil, so that as floodwaters are receding, that will go away as quickly as possible. One of the first is that I recommend for mitigation are tree lines and buffers between waterways and any field that's in production. So without this, without trees and other vegetation anchoring the soil, not only will that cause erosion, but you can actually lose acres that can just completely wash away into a body of water. So having a tree line, the roots of trees or shrubs or whatever that might be, can really do a lot to anchor the soil in place, but also can act as a way to, in the event of a flood, to slow down the flow of water before it enters a field, and can also act as a filter. So, floods can carry a lot of debris, wood and other material, crop residues from neighboring fields, and that can really filter out a lot of that. If you've ever driven by an area that's been affected by a flood, it's always amazing to me to look at the tree lines and see how much material has gotten stuck into the tree lines. And it can be a really good indication of how deep the water was as well. Another practice that I recommend is cover cropping. This can really help prevent erosion and deposition from floods in fields. And my philosophy is that for any field, it should always be green. So as soon as a field is harvested in the fall, for example, my recommendation is that you would immediately follow behind a combine with a planter or some kind of broadcasting equipment to plant cover crop seed. That would be there over the course of the winter and would be present in the springtime if there ever were to be a flood event. Cover crops have a lot of benefits in fields, and this is potentially one. So in the event of a flood that would move through an area, cover crops, the crop itself could die, but the roots and that structure that the cover crops grow would still be in place and would effectively help hold that soil there, but can also slow down the flow of water as it's going across a field. Cover crops can also be a great remediation tool. So in the event of a prevent plant, for example, where a farmer is not able to plant in the springtime, I also recommend that a cover crop would be planted as soon as that field is accessible. That they might have to wait some time for water to recede and the field to dry up enough for them to get into. But the other option is that you can use something like aerial application if it's too wet. As soon as the standing water is gone, something like an aerial applicator could go in and broadcast seed over the field to start establishing a crop for the season. And there are government cost share programs available through, like the NRCS, for example, that can help with purchasing seed and doing some type of application. And then again, cover crops in the field can help prevent additional damage to a field, through additional water or wind erosion. Can also help recover some of the other things that we talked about with topsoil and soil ecology. Cover crops are also a great way to add nutrients to the soil. So this is especially true of leguminous crops. So I always recommend a cover crop mix that would have several different species of crops. And certainly one of those should be legumes that add nutrients such as nitrogen back to the soil through natural methods. They can add significant amounts of nitrogen to the soil. And so, doing things like soil sampling at the end of a season are important just to understand what's the status of the soil, how much did a cover crop add, and then what type of other amendments might be needed in the future for other seasons. Cover crops are also very useful for recovering soil biology. If you think about all the different types of biology that we talked about earlier, such as fungi and bacteria, micro and macro fauna, all of them rely on organic matter and in most cases living plants to be able to grow and reproduce. So having cover crops in the soil are really important to help recover some of that biology that really does have a very positive effect on crop performance and yield. Lastly, the University of Nebraska does have a lot of resources for farmers, specifically focused around floods and other disaster recovery and other types of events. But if you go to disaster.unl.edu/crops, there are dozens of articles that are relevant to farming and recovery from floods. But they also have some other resources for those who might be working with livestock, specialty crops, and some other things as well that are great resources. So really what I covered in this webinar was some of the basics, but the University of Nebraska does have a lot of other information available for those who may have been affected by floods or know someone who has, or possibly have land in an area that is prone to that. If there are any questions, I'm more than happy to answer that. So I'll go ahead.
Thank you, Nate.
Yeah.
I loved your animations that you made. Did you create all the slides?
I did. Yes, all of that is mine.
That's awesome. That's awesome. Thank you for that. We do have a question here from Maya. The question is, what are the potential effects of putting sand deposits back in the river where it came from?
Sure, that's a great question. I think that for me, that one of the, I think the most obvious is that you're anytime that you're adding sediment into a body of water, you're having impacts on basically things like the amount of light that can go into the soil or into the water, and also you're causing that sediment to flow downstream. Everything goes somewhere else. So you have to think about what are the possible effects of downstream users. Where is that sediment going to end up? For here, that's the Gulf of Mexico, and they have a lot of problems with things like eutrophication, algae blooms. So anytime that you're adding sediment that could contain things like nutrients, especially phosphorus, that can have a lot of effects on downstream users. And I think really just understanding the characteristics of whatever that deposit might have been. Sand typically won't have that much nutrients that it's holding on to, but it can have some effects. So I would really, my recommendation would be to consult experts. That could be the NRCS, it could be your local NRD that would have some advice on what those options might be. But the biggest thing is that anytime that you're returning sand to a body of water, it would have to be permitted and approved.
Thank you. I had the same question as well. So thank you, Maya. Another question I had was, why was the impact of the flooding not as extreme along the Platte River? And it may just be because it's not going downstream, but it seems that the Platte River had less of an impact than the Missouri and the Elkhorn.
Sure. I think that when you look at the valley itself, that's one thing that I can think of. It's going through, I think it's more of a glacial till area, so there's a lot more elevation change when you look at kind of the southern side of the Platte River. So it does kind of constrain where the water can flow on one side at least. When you look at places like the Missouri River, also the Elkhorn River, they're pretty broad valleys with very little elevation change. And so I think in those areas in particular, the water was really able to spread out quite a bit more.
Thank you. All right, you guys, do you have any more questions for Nate? Give a few more minutes. I guess I have another question. I know that there's been studies into microbes and covering seeds with sort of a microbe cover of some kind. I'm not exactly sure, but I know that has a big impact on drought. Does it also have a similar impact on flooding?
So I think that there's a lot of science being done around biologicals and different seed treatment technology, and I think those are all very exciting. I don't know so much about flooding, but I have seen some of the research that you've mentioned about drought specifically. When I talked about things like arbuscular mycorrhiza and how they form associations with plant roots, they can really reach out quite a bit into the soil to help plants look for and acquire water and nutrients in the soil. I'm not so sure about how that would really apply in flooding. especially a longer term flood where a lot of that biology can be affected just like a crop would be.
Yeah, makes sense. Well, thank you.